Hi, this video is to go through the answers to the heat energy transfer study task that you've been working on. Your worksheet has this piece of data. We have a cross-section through the plate tectonic model, looking at a divergent and convergent margin, where we get a mid-ocean ridge with its associated volcanic activity and a subduction zone, again with some volcanic activity. The graph above, plotted to the same horizontal scale, shows us the variations in heat flow that we get across this area. Don't worry about the units for this particular graph. Microcalories per centimetre squared per second. It's just a measure of how much heat energy is coming out of the Earth for each sort of unit area every second. So there's a set of 5 questions to answer. You should already have had a go at those and come up with some answers. So let's discuss these answers. Let's see what you've come up with. The first question asks for example of the surface expression of this heat flow. What do we actually see at the surface that's caused by the internal heat and the flow of internal heat from the Earth? There are 3 key pieces of evidence, I think. Firstly, geysers. They're relatively unusual features at the Earth's surface, but places where hot water is actually thrown out of the ground into the air. Most famous of these is probably in Yellowstone, Old Faithful. They get their name from a place called the Geyser Basin in Iceland, where you can see very frequent eruptions of a geyser. But there are other places, Rotorua in New Zealand quite famously, and the places in America and Russia and a few others. The second piece of evidence are hot springs. Now this could be where we get sort of geothermal areas, boiling mud pools like in New Zealand or in Yellowstone. Or it could just be hot water reaching the surface. Most famously in this country, Bath, with its hot geothermal spring. We actually look at the geology of that in year 13. Even closer to home, there are warm springs that come out of the ground, for example, in places like Taff's Well in Cardiff. So, again, something must be heating that water. There must be heat at depth. The final example, of course, nature's big show, the most spectacular of all, the volcanoes. Too many to list. The ones I've shown here in the PowerPoint are a few of the places where we get a lava lake at the surface. Really very unusual feature. The second question then is quite straightforward, asking you to describe the distribution of the heat flow at the Earth's surface. Now I've made this a 5 marker, looking for a comprehensive answer. If this was an exam, that may only be 3 marks, for example. But we can talk about where the highest values are. And they're clearly linked with areas of volcanic activity, the ocean ridge and also the island arc. The lowest values then we can find at the subducting trench, where cold lithosphere is being pushed down or dragged down back into the mantle. The ocean basin then is sort of fairly consistently low values. If we were plotting this perhaps more accurately, we might see a gradual decrease across the ocean basin as the lithosphere, the oceanic lithosphere, gets cooler as it gets older and further away from the oceanic ridge. but we go with the data that we have. Question 3 then looks at how surface evidence of heat flow allows us to determine the mechanism of heat energy transfer. There are 3 ways heat energy can be transferred: radiation, conduction, convection. Radiation clearly doesn't apply because we're looking at solid and liquid materials. The question then is, does the Earth conduct or convect? If the Earth conducted heat energy, what we'd see around the Earth's surface is fairly constant heat flow. But as we can see from this piece of data, heat flow isn't constant. We have some areas of very high heat flow and some areas of very low heat flow. Now that concentration of heat flow is perhaps more likely to be the result of convection currents. Rising plumes of hot material are going to concentrate heat in some places. Sinking colder material will reduce the heat flow in some places. Geological processes are driven by heat, with just only a few exceptions. We know we have an external source of heat energy in the sun that heats up the Earth's atmosphere unequally, some places more than others. We get, as a result, then a pressure gradient and movement of wind, movement of air. That can be an agent of surface processes. The bigger agent, though, of surface processes is going to be the water cycle. And that, again, is driven by solar energy. As the water's moved around the water cycle, it will weather, erode, transport, deposit sediment as it's moving. Finally then, to lead us on to work we're going to be doing in a week or two's time, we only have localised areas of the mantle melting. Now, in general, the temperature of the mantle isn't high enough to melt rock. We've seen that in the lesson that you did on the geothermal gradient. So something has to change, something has to be different for rock to melt. And it's going to be one of two things. It's either got to be something that's going to increase the temperature of the mantle locally, or something that's introduced to the mantle that might lower the melting temperature of the rock material that's there. Now, a mantle plume will locally increase the temperature, maybe 150 degrees centigrade higher than we'd expect it to be. That could cause melting. Or subduction zones will take water down into the mantle. That water will reduce the melting temperature of the rocks at depth. And eventually, if it reduces it enough so it's below the temperature of the geothermal gradient, we'll get some melting starting. So, as we look at the eruption of Strokor, a geyser in the Giza Basin, to draw our conclusions. This heat flow is crucial for understanding how the internal processes of the Earth work. In particular, we need to be thinking about the factors that can cause rocks to melt. Why do we get magma forming in localized areas? Magma isn't formed everywhere in the Earth, it's only in some places. So we need to consider carefully the geological processes that create that magma, create the conditions for melting in those particular locations, those particular tectonic settings. More of that to come. I'll see you then.